Welcome to This Explainer. Have you ever wondered how massive power grids flawlessly distribute electricity to an entire city, or how the tiny, intricate circuits inside your phone manage complex currents without just shorting out? Well, it all comes down to specific network shapes. If you're starting electrical engineering right now and feeling a bit overwhelmed, take a deep breath. You are in exactly the right place. We're keeping things calm and focused today. No high-pressure lecture here. Instead, we're just going to gently shift our perspective on how we look at complex electrical networks.
So you're working through a problem, looking for that one easy starting point, and boom, you hit a complete dead end. You trace the current, really hoping to find a clean series connection or maybe two branches sharing the exact same nodes for a parallel one. But instead, the current just splits and intersects in ways that completely break all our comfortable, predictable rules. It is incredibly frustrating when those basic principles just fall apart on the page. I completely validate that feeling. But hey, it doesn't mean you're missing something obvious. It just means you need a different mathematical tool to process what's happening.
Let's look at how this dead end actually happens. Imagine a 100-volt source connected to a bridge network. The current leaves the source and immediately hits a crossroads, splitting into two paths. But before those paths can neatly return, they hit another intersection, with a resistor bridging right across the middle. Because of this interconnected web, you literally cannot group the top resistors together or the bottom ones. The traditional rules are entirely entangled in the bridge. The current is splitting and converging in a way that aggressively blocks our standard reduction methods.
Section 1. Meet star and delta. Recognizing the shapes.
Okay, to untangle this mess, we need to introduce two key network formations. First up is the delta-connected network. True to its name, it forms a closed triangle or loop. Current is completely free to circulate within that closed path between three distinct nodes. Now, contrast this with the star-connected network. A lot of people call it a Y connection. Here, the branches all meet at one single central point where all the internal currents converge. Right now, seriously, do not worry about the math. Purely focus on visualizing these two distinct pathways.
You might be wondering, why does spotting these specific shapes even matter? Well, because real electrical networks rarely fit into neat little boxes. Think about the global power grid. Power plants often generate electricity in a star configuration to establish a safe, neutral ground point. But when they transmit that massive power across vast distances, they shift to a delta configuration to save entirely on the cost of running a neutral wire. So from massive grids to everyday electronics, we absolutely need reliable tools to mathematically untangle these exact shapes. Section 2. The shape-shifting trick, transforming the circuit. To move past our dead end, we actually have a really cool shape-shifting trick up our sleeve. We can mathematically replace a delta loop with a star configuration, or vice versa. When we convert from a star to a delta, we eliminate that central converging node. It's a node reduction technique. Going from a delta to a star introduces a central point. We are fundamentally altering the internal geometry here, but here is the absolute magic of it. The terminal voltages and the total current entering and leaving those outer points remain perfectly identical. The rest of the circuit is entirely unaware that the shape inside has shifted.
Now, when you see the equations for this, please don't panic. Guide your eyes away from trying to memorize a dense alphabet soup of variables. Instead, calmly look at the mathematical logic. For example, to convert a delta into a star, you just take the two adjacent resistors touching your outer node, multiply them together, and simply divide by the total sum of all three delta resistors. That's it. It's entirely proportional. Adjacent times adjacent divided by the total sum. It's just a visual pattern.
And here is a beautifully simple shortcut that makes this even easier. When you have a balanced network, meaning all three resistances are exactly equal, the equivalent delta resistance is exactly 3 times the star resistance. This isn't just a clever textbook trick either. Balanced networks are the absolute standard in real-world power engineering. So if you have equal resistors, you can skip those proportional equations entirely. Just multiply or divide by 3 depending on which way you're shape-shifting.
Section 3. Finding the flow. Untangling the bridge.
Let's take this newfound trick and apply it back to our initially stuck problem. When you're sitting in an exam, just break the workflow into these 3 highly manageable, low-stress steps. Step 1, visually identify the delta or star. Step 2, run the conversion pattern to shapeshift it. Step 3, take a breath and enjoy the fact that your circuit is opened up and everything has beautifully returned to the comfortable series and parallel rules you already know.
Jumping straight into the action with our bridge circuit, take a look at the top triangle formation. It's made of 3 distinct 9-ohm resistors. That is our delta. And because they are all perfectly equal, our magic rule of 3 applies effortlessly. We don't need dense fractional equations. A 9-ohm delta converts cleanly into a highly manageable star, where each single branch is just 9 divided by 3, which is 3 ohms. No complex fractions, just a simple, elegant shift in our perspective.
By dropping that newly calculated 3-ohm star back into the overall circuit, the formerly impossible bridge completely opens up. Trace the new current flow with me. On the left branch, the new 3-ohm resistor sits cleanly in series with the original 6-ohm resistor. There are no competing crossroads there anymore. On the right branch, the other new 3-ohm resistor is in perfect series with the bottom 3-ohm resistor. The complex node interactions are just gone. We already know exactly how to solve this.
Let's run the final numbers step by step to see it all the way through. On the left branch, 3 ohms plus 6 ohms gives us 9 ohms. On the right branch, 3 ohms plus 3 ohms gives us 6 ohms. Now we have a straightforward 9 ohm and 6 ohm resistor sitting perfectly in parallel. Using our standard product over sum rule, 9 times 6 is 54, divided by the sum of 15, which perfectly equals 3.6 ohms. Add the top 3 ohm stem from our star, and our total equivalent resistance for the entire massive network is just 6.6 ohms. Divide our 100-volt source by 6.6 ohms, and we get a satisfying 15.15 amps.
Section 4. A shift in perspective, your practical takeaway.
As we wrap up this study session, let's look at a few low-pressure takeaways to carry into your next assignment. First, always focus on the visual pattern of the transformation, adjacent times adjacent over the total sum, rather than memorizing letters that change from textbook to textbook. Second, never hesitate to completely redraw the circuit when you hit a dead end. Seeing it cleanly on the page works absolute wonders for your brain. And most importantly, if standard rules fail, take a breath and simply look for a way to shift your perspective.
Complex networks don't require complex panic, just a new perspective. It's an incredibly empowering way to approach problem solving. But before we go, consider this. We just used the shape-shifting trick to mathematically alter internal nodes in a simple direct current resistor network, right? What do you think happens when we swap those steady resistors for capacitors and inductors in a high-frequency, constantly oscillating AC circuit? Does the shape-shifting trick still hold up when time and phase shifts enter the equation? Think about it. Keep practicing, trust the visual patterns, and I'll see you in the next explainer.